All right. Good afternoon again. Maybe some of your classmates will be coming in later. But I'll start because this would be quite a loaded day, and I want to finish all the lectures this week so that next week you'll be free to work on the project. I'll tell you the final project from me probably next meeting, or if really needed, we can still meet on the 23rd so I can give you a briefing about the final project, and then you will still have that week plus the 29th until June 9th to have your final project prepared. But I think the deadline for the final project, at least from my end, could be scheduled during the finals week so that you'll have lots of time to do it. Especially, I know you do have other courses in mind, so you might have other projects or final exams coming up. So I don't want to add too much to that pressure, you know. So yeah, for today and on Thursday, I want to talk about classification and clustering algorithms in machine learning, at least the basic ones, to give idea to those who are not really into data science to look at what are these algorithms for, at least have some sense of how they work, at least what's the math behind them. I will not focus much on the coding because, for instance, I'll provide you with the MATLAB codes which are really sort of one-liner commands, but to have a structure to the program, you'll just add some uh, some codes that will plot the figures, that will visualize the data. But essentially, these are intrinsic commands in MATLAB, so we'll not be really into the coding of it. What we'll try to do is to build an understanding of how these methods work and what are the different options that we can use depending on our data. So I don't want to yeah those well into data science might be disappointed about that I'll be talking about just the simple algorithms, but it's really an introductory course for people from various fields. So I guess that's more appropriate to talk about the basic ones, right? So as I mentioned, this will be about clustering and classification algorithms. They are quite similar. Clustering algorithms are more of unsupervised machine learning techniques. When we say unsupervised, you don't provide your algorithm with a key to the clustering or to the classification of the data. While when we say supervised learning, you are giving the classification to the training data to your computer so that it will learn from there, right? So the idea is, say you have the data, if you have these points in space, I plotted them as points in space. When we have a clustering algorithm, the idea of the cluster, the purpose of clustering algorithms is to, based on the data or information about the data, it will try to group them into several clusters. And as I've mentioned, these are usually unsupervised learning, machine learning approaches, wherein we don't tell the machine what is the real clustering of this data. We assume that we don't have any knowledge about the clustering of this data. So our machine learning algorithms will say, decide, okay, this data are similar with respect to some measure. So the machine will tell us this is probably the first group, and this would be probably the second group. So these are very useful whenever you have a lot of data and you don't know what their classification, what their groupings are, or which are connected to which. On the other hand, classification algorithms are quite similar, but these are usually supervised learning methods. The idea is not to group the measurements together, but or the data together, but to classify to which group they would belong. Usually classification algorithms has some sort of clustering into them. So the idea is, okay, this may be group one according to a clustering algorithm. This could be group two according to a clustering algorithm. And then you have a query point, say this guy. And the idea of classification algorithms is to predict to which of the two clusters will this test point or this query point will belong to, right? Either to group one or group two. But to perfectly or to understand this machine learning algorithms, you want to take a look at what are the different notions of distances and metrics that are used by these algorithms. These terminologies will also pop up in the programs that we'll be seeing later. So I want to discuss them a little bit, right? So I'll have an introduction here to distances and metrics. Because basically, most algorithms has the following idea. So let me just fix the grouping here. For instance, this is the first group, the blue group, and say this is the green group. Okay. Okay. Now, if you want to classify a certain data, or even clustering, clustering really intuitively it means grouping together data that are close to each other, right? So it is grouping according to proximity. But how do we define closeness? How do we define how near are two objects from each other? Okay, so there would be several measures of distances. And on the other hand, when you do classification, say my query point is this purple one, right? The idea is I will measure how far is the purple point from the blue group and how far it is from the green group. And which one is closer would probably be the class to which the purple point will belong to, right? But again, that measure of closeness or to which cluster that point is closest to will depend on some measure, some measure that you define or some measure that you will ask your program to use. So let's start with a brief overview of what are these distances and metrics that you can use. The first one or the first class probably would be the Minkowski distance. Minkowski distance. Minkowski distance, these are distances that are norm-induced. So these are norm-induced metrics or distances. Okay. So when we say norm-induced, not norm, but norm-induced. Oops. When we say norm-induced, there is a defined norm on your vector space. So for those who know linear algebra, you have a vector space, and then we can define a norm on those vector spaces. So let's say x and y are vectors. So these are vectors. These are a bunch of numbers that are grouped together, and we can define the distance or the Minkowski distance between x and y. Let's call the distance little d. The distance between x and y is actually just the norm of the difference x minus y. And this guy where this measure is a norm. Now, for those who are not familiar with what a norm is, basically a norm is just a function that assigns to each vector a non-negative real number, satisfying the following properties. So maybe we can say a norm satisfies the following property, or the following properties. Number one, zero property. The norm of a vector is equal to zero if and only if it is the zero vector. So only the zero vector possesses the zero norm, okay? The next one is what we call absolute homogeneity. Or the first one is the positive definiteness of the measure or the function norm. Now, the next one is absolute homogeneity, which just tells us that if you have a vector x times a scalar lambda, when you take the norm of their scalar product, that is just the absolute value of the scalar times the norm of the vector, all right? So that means it is scaling invariant. If you multiply a norm by a constant, the length, so you can think of the norm as the length of the product is equal to the product of the norm of the original vector times the absolute value of the scaling constant. The third property, this is something you're familiar with, the triangle inequality. So this tells us that the norm of x plus y is less than or equal to the norm of x plus the norm of y, right? Hold on. So if you can define a function from the vector space towards the set of non-negative real numbers that will satisfy these three properties, then you have a norm. Now, once you have a norm, you can define the Minkowski distance. The Minkowski distance between two vectors in your space is simply the norm of the difference between the two vectors, right? So this is a general class of distances, Minkowski distances. Now, usual Minkowski distances are as follows. These are the usual Minkowski distance. The distance between vectors x and y, all right? Or maybe let me just first write the notation for the vector x and y. So we let x to be the vector x1, x2 until xn, and y be the vector y1, y2 until yn. It could be a column vector, it could be a row vector, it doesn't matter. So you have two vectors, x and y, with component x sub I and y sub i's, right? Then the usual Minkowski distances are like this. So the distance between x and y is equal to the summation of the absolute difference between corresponding components. So you take the difference between components, corresponding components of x and y, you take its absolute value, then you raise it to the p power, to the power p, and then take the summation from 1 to n, and then raise it to 1 over p, where p is a number from 1 to positive infinity. 1 is included, and positive infinity could also be included too. So these are the usual Minkowski distances. So the distance between two vectors would be computed as taking the difference of their corresponding components, and then take the absolute value, raise all of them to the p power, and then take the summation, and then raise it to 1 over p. So that's your Minkowski distance. There are three usual Minkowski distance, and these are things that the MATLAB understands. First is when p is equal to 1. We call this the Manhattan distance. Or probably to illustrate this, let's consider two vectors, right? So, for example, let's take, say, x to be the 3-vector 1, 1, 1, for instance, and y is the vector 2, 0, -1, for instance, right? Now, the Manhattan distance is the Minkowski distance when p is equal to 1. So that means the distance between vectors x and y under the Manhattan distance, also called the taxicab distance, is the summation from 1 to n, the number of components in your vector, of x sub I minus y sub I, right? So you just take the sum of the absolute differences, right? And this is obtained from the general Minkowski formula when we take p is equal to 1. So this is 1, this is 1. So the formula will be reduced to this guy, right? So in our example, our Minkowski distance would be 1 minus 2, that's -1. In absolute values, that's 1. 1 minus 0, 1, absolute value is 1. And then 1 minus -1, that's 2. Absolute value of 2 is 2. So the distance between 1, 1, 1 and 2, 0, -1 under the Manhattan distance is equal to 4. This is called the Manhattan distance or the taxicab distance because it's like the meter of a taxi in a city with rectangular blocks. So for instance, this is your blocks. Well, for instance, your taxi is here and your destination is here. So the total distance you travel is this guy from here till here till here, right? Because it sums up how much is the displacement in the x-axis plus the displacement in the y-axis plus another displacement in the y-axis. Hold on, sorry, somebody's calling me. Hold on. Sorry about that, but that's the reason why it is called Manhattan distance. So you really you can imagine you're a taxi that is traveling in a rectangular city block arrangement. So how the meter of the taxi ticks, that's how you compute the distance. Okay, so that's the Manhattan distance. Another common distance or a common Minkowski distance is the Euclidean distance, which is we are very familiar with, hopefully. So that's the case when P is equal to 2. So this is the Euclidean distance. And again, to get the formula, you simply replace all the P's in the Minkowski formula by 2. So that means the distance is just the summation of xi minus yi quantity squared, I going from 1 to n, raised to the 1/2, which is basically the square root of the sum of the squares of the differences, all right? So if you compare it to the Manhattan distance, the Euclidean distance is really looking at the distance of the shortest path, right? So that means you connect the 2 points that of which you're computing the distance between by a straight line, and you look at how long that line is, right? So this is the Euclidean distance P equals 2, and then the original one is the Manhattan distance P equals 1, right? So you see how different these two distances are, okay? So in our example, well, the Manhattan distance will be the square, the Euclidean distance will be the square root of the squares of the difference. So that means we have 1 minus 2, so that's -1 squared, so that's going to be 1. Then 1 minus 0, that's 1 squared, so that's going to be 1. And we'll have 1 minus -1, that's 2 squared, so we'll get a 4. So this will be square root of 6. That's the Euclidean distance. So you see, these distances will give us different numbers. But for some applications, Manhattan distances are more appropriate. For some, the Euclidean distance are the ones to be used. All right. Now, the third Minkowski distance that might be of interest to us is the case when P is equal to infinity, which is a limiting case. This is called the Chebyshev distance, or the Chebyshev distance. Okay. And the formula for this is this guy. This would be the distance between x and y would be the maximum of the pairwise differences. So instead of summing them up and taking summing up powers of the absolute differences and then taking the power 1 over p of the sum, you simply take a look at what is the largest absolute difference among the components. So in our particular case, for the Minkowski distance, you have two options. The first option is this, the horizontal displacement or the vertical displacement. Whichever is higher, that's gonna be our that would be our Chebyshev distance. So it looks from the drawing that the vertical displacement is higher. So this is what I'll call the Chebyshev distance, the case when p is equal to infinity. Okay, so that's the Minkowski distances. But not all distances are Minkowski in nature or norm-induced in nature. There are some nice distances that are not defined by some norms. So for instance, we have what we call the Hamming distance. The Hamming distance is usually used for information technology applications or for comparing data strings. So basically, the Hamming distance counts the number of points at which two corresponding pieces of data can be different. For instance, I have the string hello world, the classic first exercise for programming courses, and say I have Hera Powell, right? And I want to compute the distance, quote unquote, between these two strings of characters, right? Now, the Hamming distance just computes in how many bits or in how many characters these two strings will differ, right? In the first place, have both h's, so that will contribute nothing in the distance. They have e in the second places, but they differ here in the third, in the fourth, in the fifth, and then on the sixth, on the eighth, and on the eighth, right? There are 8 characters that are different from these two strings. Oh, sorry, not 8. There are 5 different characters in these strings. So we say that the Hamming distance between them is 5 because they differ in 5 spaces, right? So really here, the ordering is important. You compare those characters in the same position. So if they do not differ, then you don't count them in the Hamming distance. So it's really just the number of characters at which they differ. It's also used whenever doing working with digital files. So if you have files that you have turned into a binary file, to say you have 1101, 1001, and then you have another file or another data that is of the form 1001, 1101. To get the Hamming distance again, you can simply count the number of characters at which they differ. Or you take the sum of the two, right? Because the sum of two same characters in binary is just equal to 0 if they are exactly the same. If they differ, then the sum is 1, right? So for instance, here, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 0 plus 1 is 1, then 1 plus 1 is 0, 1 plus 1 is 0, 0, 1, 0. So there are 2 non-zero bits, so the distance here is 2. Or you can just simply count in how many characters they differ, then that will also give you the Hamming distance. All right. So if you're if you're clustering words, right? You took a dictionary and then you want to cluster words, you can use the Hamming distance. But there are certain programming languages handle Hamming distances differently whenever characters are of different lengths. So be careful about those cases, right? So these are this is the Hamming distance. Probably third distance that I will share with you would be the cosine distance. Now, if you remember your elementary calculus, you dealt with the angle between two vectors. So if you have vector x like this in standard position, and you have a vector y in this position, we can define the distance between them in terms of the angle between them. So this could be our measure of distance. So basically, if you do not care about the lengths of the vector, but you're just looking at how far apart are them in terms of angles, then you use the cosine distance, all right? Now, to use the cosine distance, we need to define first what is the cosine similarity. The cosine similarity is basically just the cosine of the angle between the two vectors. So this is the angle or the cosine of the angle between the two vectors. So in this case, the angle between them is theta. So the cosine similarity, let's say it's C sub S for cosine similarity between vectors x and y. From elementary calculus, this is computed by the dot product of x and y all over the length, the Euclidean length of vector x times the Euclidean length of vector y. In other words, this is just the summation of xi, yi, I going from 1 to n, all over. The lengths would be the sum of x sub I squared, I going from 1 to n, quantity squared, sorry, not quantity squared, raised to the 1/2, times summation of the absolute value of y sub I squared, I going from 1 to n, and then raised to the 1/2. So that's how we compute the angle or the cosine of the angle between two vectors. So in data science or in terms of distances and metrics, we call this the cosine similarity, right? Which is basically the cosine of the angle between two theta, right? So in other words, maybe I could illustrate it a little bit more better here to illustrate what's the difference between cosine similarity and other Minkowski distances. So say my next vector would be y, right? If we're talking about distances, Minkowski distances, we'll be interested with this endpoint and how literally apart they are. If we have p equals 2, then this would be the length of the straight line joining them. If I'm using taxi cab distance, look at the vertical displacement, add it to the horizontal displacement, that's the distance between them. But whenever talking about the cosine distance, I don't care how long one vector is. I don't care how far apart their terminal points from each other are. What I'm really interested is the angle between them. Or I'm looking at the distance between them as a function of the angle between them, right? Now, the distance, the cosine distance, maybe we can call it d sub c. The cosine distance between vectors x and y is simply 1 minus the cosine similarity between x and y. And let's see why this matters, right? Now, if your if your vectors are in the same direction, meaning if they overlap, right? So that means the angle between them is exactly 0. And the cosine of 0 is 1, so the similarity is exactly 1. So this is perfect similarity, perfect cosine similarity. That's the perfect correlation between the two, because the two vectors are overlapping at each other. Now, two vectors, if they are, say, orthogonal to each other, or if they are at 90 degrees with each other, so the angle is 90 degrees, cosine of 90 degrees is 0. That means the correlation between them, or the cosine similarity between them, is equal to 0. That's when they are orthogonal to each other. If they're opposite to each other, if this is vector x, this is vector y, the angle between them is 180 degrees. Put that inside the cosine, so that will give you -1. Or if they're really opposite each other, you can compute that this guy will give you -1, right? So this is the least cosine similarity that you can get, -1. So cosine similarity ranges from -1 to 1, as it should be, because that is just the cosine of an angle, right? A value of -1 means they are opposite each other. A value of 0 tells us that they are at 90 degrees with each other. A value of 1, perfect similarity, means they are in the same direction of each other. Now, when we look at distances, when they are perfectly correlated, if they are in the same direction, then the similarity is 1, so the distance between them is 0. So if I have a vector that are overlapping but of different size, of different lengths, then the cosine distance between them is both equal to zero. The distance between them is equal to zero, but the Minkowski distance will not be equal to zero because you need to compute how far the endpoints are from each other. Now, if they are orthogonal to each other, the Minkowski distance is equal to 1 because you'll have 1 minus 0. Sorry, the cosine distance will be equal to 1 minus 0. That's equal to 1. Okay. And then if they're opposite each other, if the vectors are opposite each other, so we know that the cosine similarity will be -1, right? So they will be at distance 2 from each other. So essentially, the cosine distance, which technically is not a distance in the technical sense, right? Because you don't have positivity here, but essentially, its value ranges between 0 and 2, right? You get the distance 0 when they are in the same direction. So really, if the kind of data you're measuring, or you want to classify, or you want to cluster, really you want to look at the trend rather than the actual measurements. Then you use cosine similarity or the cosine distance to measure that. Okay, but be very careful because there's a very different playing field where the cosine distance is being used. Okay, and the last one is the Pearson correlation, or correlation similarity. This is basically R equals summation of x sub I minus the mean x bar times y sub I minus y bar as I goes from 1 to n all over the square root of the summation of x sub I minus y sub I squared, I going from 1 to n, times the summation of y sub I, sorry, not yi, it should be y bar, x bar, and then this is y bar, quantity squared, I going from 1 to n, which is related to your statistical measure, the Pearson R correlation coefficient. So this is really looking at the correlation between these two guys, or between the vectors x and y. But in this particular discussion, I'll be working with Minkowski distances, Hamming distances, and cosine distances a lot. Okay. Now, any questions about this type of distances? Of course, this is not an exhaustive list. There are other measures of distances, but these are the ones that we will be using in the programs that we'll be exploring today. Okay. I'm wondering what happened to your classmates. I'm thinking, did I announce that there are no classes today? I don't think so, right? So yeah, probably they got lost in whatever Zoom meeting, but I hope they can watch this recording because the final project will be about using clustering and classification algorithms on your choice of data. So that's why I want to really finish discussing these algorithms this week so that you can start working with your final project. Okay. Now let's go to clustering algorithms if there are no questions about distances. Again, in clustering algorithms, or these are unsupervised machine learning algorithms, wherein we train our algorithm to predict the clustering or the grouping of ungrouped data that we will feed into it. So we have some sort of data, and then we want our algorithms to give us output the most probable insofar as the algorithm is concerned grouping of this ungrouped data that we will be giving it, right? Now, there are three most commonly used basic clustering algorithms. We'll discuss them one by one. I don't know what is the most efficient way to do it. I'll discuss all the algorithms first before going into MATLAB, or should I illustrate one after the other? Let me see. Yeah, I'll think about that as we go along, but I'll discuss three clustering algorithms. The first one is called hierarchical clustering. Did I spell it right? That's a problem when doing something handwritten. There's no there's no spelling check. No, it should have a single H. So yeah. Okay. Hierarchical clustering. So in hierarchical clustering, it is really you want to cluster or you want to group your data, but you have a feeling that there are some embedded structure within the data. So you don't just want to cluster them and look at the final product. It's probably that you have some ideas, some outside information or some feeling that there could be some embedded grouping within the clusters. So maybe there's a subclustering or there's a hidden structure within your data. So if that's the case, then hierarchical clustering will be the one that is best used. Because here you can really discover these hidden patterns because this starts the clustering from bottom up. Okay. Now the thing here is we want we need to know how many clusters there are or what is the maximum number of clusters in your data. So say so here you should know or it should be given the max number of clusters. So let's call that variable K. So if you know that you have say 100 data, and then you know that there could be at most 5 groups in there, and there are hidden structures that you want to, or hidden patterns within the clustering that you want to also have an idea about, then you use hierarchical clustering, right? I'll illustrate it, but with a fewer number of points, just for brevity of illustration. Because the idea is very simple. So say you start with, say 4 data. So say you have n equals 4. You have 4 data points. And then we say that you have at most 2 clusters. Now, the first thing to do is we consider or we treat each of the points to be a cluster. All right. So there are tentative clusters. So this is cluster 1, cluster 2, cluster 3, cluster 4. And then we compute the inter-cluster distance. In the case of in the starting case or in the starting iteration, that would be easy because each cluster is composed of only 1 point, right? So since each cluster is composed of only 1 point, then we simply compute the distance between the points. That's what is meant by measuring the distance between clusters. So this is tentative cluster 1, tentative cluster 2, cluster 3, cluster 4. We need to move on and continue until we have hit the maximum number of clusters. So there are still 4 clusters here. Each cluster has 4 points. So we first compute the distance between the clusters. And then you need to decide what type of distance will you use. Will you use a Minkowski distance? In that case, which Minkowski distance, a Manhattan, a Euclidean, or a Chebyshev distance? Or will you use a Hamming distance, or you will use the cosine distance, right? So it's up to you depending on what type of data that you have. So you compute the intercluster distance, and then you group together the two closest clusters. So for instance, you compute the distance and noted that this guy and this guy are closest to each other. So you will collapse them into one cluster. So this would now be my tentative cluster 1. This is my tentative cluster 2. And this is my tentative cluster 3. Right? And then there is still work to be done because we are expecting only at most 2 clusters. And here we are, we still have 3 clusters. Now you proceed again with another iteration. So the next iteration is again to compute the intercluster distances. Now it could be a little tricky now because one of our clusters has 2 points already. So you have to decide what type of distance, or how do you compute the distance between a point and a cluster. There are several ways to do that. Of course, you will decide what's the underlying distance, but there are some options to compute the distance between clusters comprising of more than 2 points. The first one is called the I don't know how MATLAB called it. I forgot, but we can take a look at it later. It's, I guess, you compute the you assign the distance between clusters to be the distance between closest neighbors. So you get the pair which are closest from cluster 1 and cluster 2. So 1 point in cluster 1, 1 point in cluster 2, so that those 2 points are the closest neighbors between interclusters. And then the distance between those 2 members or those 2 representatives could be assigned to be the intercluster distance. Or you could have a complete linkage computation. The complete linkage computation is that when you compute the distance between the 2 clusters using the most remote points. So you will consider all the possible pairings of elements of the clusters, and you look at those that pair which is most remote from each other. One from one cluster, one from the other cluster. And if you're guaranteed that they are farthest from each other among all other pairings, then you take the distance between those 2 points, then that will be the point, that will be the distance between the clusters. Or another way is to compute the centroid or the average of the 2 clusters and get the distance between the averages. So that could be the way to compute intercluster distance. But in any case, however you compute the intercluster distance, you compare again the intercluster distance, and the clusters that are closest to each other will again be collapsed into one bigger cluster. So for instance, if it so happened that this point or this cluster is nearer to this cluster than this one, then we will join them together to form the second cluster. Right? And then we will stop the algorithm because now we have hit the maximum clusters. Or you can still continue, right? Because K is the maximum. So you can again compute the intercluster distance, but that will not be useful in this particular case because there are only 2 clusters left. Then definitely they are closest to each other by default. Then you will collapse them together. You will only have 1 cluster, right? But that's how hierarchical clustering works. Yeah, easy enough. I hope the principle is easy because we don't have to care too much about the programming of it because we will just be using pre-packaged programs for this clustering algorithms. And the thing is, we'll just play with the distances that we can use in these algorithms. Okay. Right. Any questions about hierarchical clustering? Okay. So if there are none, let's go to the next. The next one is called the density-based clustering. Oops. In density-based clustering, right? One of its selling points or distinguishing properties against hierarchical clustering is that this can weed out the noise from your data, because in hierarchical clustering, all the points matter because we're computing inter-element distances and then intercluster distances. Everything seems relevant. All of the data points seems relevant. But in real life, there are there are many situations. In fact, most situations tells involve noise in the data. Some there are some outliers, and we don't want the outliers to dictate how the clustering works. Now, if you are sure that your data is tainted by outliers and don't want the outliers to influence the clustering, then you use density-based clustering. For density-based clustering, there are two parameters that are needed. So you should be given, say, a radius epsilon and a density theta. So these are two parameters that are needed. And you may notice that there's no mention about what's the maximum number of clusters. In fact, another advantage of the density-based clustering algorithms, they do not require a knowledge or information about how many clusters should be formed. It will decide on its own how many clusters will be created, right? You only need to give it a radius and a density. What are these two parameters for? Well, say you have a bunch of data points over here. Okay. And then let's say we have an outlier over there, right? So suppose these are our data points. Okay. Now, what you will do is for each of the data points, for each X in this data set, we'll compute the number of elements within radius epsilon to that particular point. So say this is my test point X, right? So maybe I'll label it with a blue one. So that's my point X. So I will first compute n epsilon of X. And n epsilon of X is the number of data points. So let me color this X. That the blue dot is my X. So for every X, for every point in the data set, you compute the number of elements in the data set that is within epsilon units away from X. So that's why it's important that you give a not too large value for epsilon, because if the value of epsilon is too huge, we cannot read out the outliers. So say my epsilon is like this. So I can create a circle of radius epsilon. Oops, sorry. I have a circle of radius epsilon, and I'm gonna count how many elements are there inside the circle. So in this particular case, I'll have 1, X itself, 2, 3, 4, 5, 6. There are 6 elements for that particular X. And you will do this for all of the data points in the set. So for every X in your data set, you will compute the number of neighbors that are within epsilon radius of that point. Okay? Now, if n of x, so in this particular case, n is equal to 6, you do this for every point, you tabulate the numbers, and then you decide whether that point is a core point, a border point, or is just noise. There are 3 possibilities. Now, here's our decision construct. So if the number of neighbors excluding itself, so you subtract 1, I'm subtracting 1 just to make sure that I am not counting X itself. So the number of neighbors minus 1. If this is greater than or equal to theta, where theta is the density that you declared before, right? So this is basically the threshold. How many neighbors should be there so that it is not considered noise, right? So you want theta to be not too large, because if theta is very large, then everything will seem to be noise, all right? Because you do not meet the number or the threshold of the density within the neighborhood of your point, right? So if this quantity is greater than or equal to theta, then we say that X is a core point. It's a core point, meaning there's a substantial number of data points in the set that lives or that accumulates within a small neighborhood of the point X. Now, if X is not a core point, but it contains, but it is part of a core point's neighborhood, then it is called a border point. For instance, say this point. So this point belongs to the neighborhood of the core point X. For instance, here my theta, for example, is 5. Sorry, yeah. Suppose my theta here is 5. And then the X that I selected here is a core point because it has 6 minus 1 neighbors. So it has exactly 5 neighbors, exactly the value of theta. So X is a core point. But say if I consider this Y, if this is Y, and I construct the epsilon neighborhood of Y, how many elements are there? 1, 2, 3, 4. I subtract 1 so that I don't count X itself. So there are just 3 members within the epsilon neighborhood of Y. So that means Y is not a core point, but Y belongs to the neighborhood of the core point X, then Y is called a border point. Right? Then the third decision point, else, we say X is a noise. Now, for instance, this guy, let's call it Z. It doesn't have any neighbors, so it's n epsilon of X minus 1 is 0. Definitely that's less than the theta that I have set earlier, that's 5. And it doesn't belong to any neighborhood of any core point, so that this is a noise. And whenever using density-based approaches, this guy will not be included in the clustering, right? Now, so you can here we have classified points into being a core point, a border point, or a noise. Now, how do we do the how do we do the grouping? Well, the idea or the criterion is just this. So if 2 core points share border points, then they are part of the same cluster. Right? So you have core points, and then if they do have common points, then they will form the cluster. Not just the core points themselves, but their entire neighborhood. So if 2 core points intersect, so they do have some common border points, then they should be part of the same clusters, right? Now, whenever using density-based approaches, or by the way, this criterion varies per algorithm. This specific clustering criterion is what we call the DB scan method. So this is the density-based spatial clustering of applications with noise, or DB scan. So that's the DB scan algorithm. Now, whenever using density-based approaches, we can create some convex, some clusters that are not convex. So for instance, you can see some clustering that look like this. So they might belong to the same cluster. but you might have some data points embedded like this, and then you have another cluster like this, and the outliers are all over the place. And we didn't consider them at all. Because again, in density-based algorithms, if you do not have enough number of neighbors, or if you don't have an influential neighbor, then you are considered an outlier and you will not be included in the in the cluster. Right. So that's the density-based approach. The third approach is the k-means clustering. Now, if hierarchical clustering reveals hidden structures within your data, and DBScan works well with outliers and within a known number of clusters, k-means try to find a consensus within the full data set, right? So it doesn't discover and ignore noise. So the idea here is we choose k central points, or what we call means. That's why it's called k means. So you should be given the number of clusters. Okay. Now, let's say that's the variable k. Then let's have some data points here. So k is given. So for my illustration, say my k is equal to 3. Okay. Now, I will initiate the process by choosing k-means. That's why it's called k-means clustering. So k-means or k-centers, k-central points. So I'll choose 3. Maybe I'll choose this guy to be my first center. This would be my second center, and this is my third center. There are different ways to choose these centers. The first one is the 4G method, or the 4G method. So the 4G method, here we just randomly select k-means. Randomly select k-means. And that's what I did here. I just randomly selected 3 points to be my central points. Now, there's a more systematic way of choosing or initializing the central points. For instance, one method is the random partition method, wherein instead of randomly selecting k-means, I will randomly group the data into k clusters and compute the average or centroid of each cluster. So mathematically, it's just the average. So you have vectors, and then you compute the average of the vectors. So that will be what we call the centroid of the cluster. And they will be the central points. So, but in any case, whether you use the 4G method or the random partition method, you get the k means or k centroids, okay? Then the idea is we compute the distance of each point to each of the 3 centroids that we have in this particular case. For instance, so you decide again what kind of distance you will use. So say I am at this point. I'll select which of the 3 centroids is closest to this point. Is it this guy, or that guy? The closest centroid will be the group that I will attach that particular point to. So for instance, if this guy is closest to this cluster, then I will put it in that particular group. Maybe I should color them differently. So say I'll color it red, for instance. So it's a red. Now, if this point again is closest to the red centroid, then it will belong to the cluster of that red centroid. Now, for instance, this one, this is the dark green centroid, and these are the points that are closest. Oops. Right? Oops. Yeah. So I'll consider this point. I'll measure its distance between the three centroids. If I discover that this point is nearest the green centroid, then I will put it in the green group, and so on. So you do this for every point and see to which centroid each data point is closest to, and you put that data point in the group of the nearest centroid. Okay, and then the next iteration will start by computing the centroid of the group. All right. So for instance, you already have three groups. So I have the red group, say over here. This is the red group. And then I have the green group over here. Okay. And then next I'll have the purple group, say over here. Okay. Now the next iteration will work by computing the average of each of the clusters. So say the average of the red group is, say, over here. I'll mark it with a star. Next, the average of the green group is over here. And the average of the purple group is, say, over here. Now, those three centroids, those three averages will be the new centers. And then I will repeat the process of taking each point, measuring their distance from each of the centroids, and then choosing which is the nearest centroid. And I will attach that point to the new centroid. Okay. For instance, if it so happened that this point now is nearer to the green centroid, to the new green centroid, than the new purple centroid, then this guy will be transferred from the purple group to the green group. If that is closer to the purple, to the green new centroid, then the new purple centroid, right? And then you continue the process over and over again until no changes in the grouping happen. And that's when we say the algorithm converged, right? So that's k-means clustering. So I hope you will agree that in principle, in theory, these methods are pretty straightforward, right? But programming them could be a little tricky, especially if you're not into computer programming. So, and I don't want you to be hindered by the fact that the programming might be tricky. So at least I hope you understand the idea behind the method, and then I can share with you some codes that will implement this particular algorithms, right? So, but first, let me know if you have questions with these three algorithms: hierarchical clustering, density-based clustering, or the k-means clustering. Right? No questions? So let me switch to MATLAB. So I'll start sharing here. And then I'll share my screen. Maybe I should share my full screen, share. And then I'll have MATLAB over here. Let me just clear everything. So I hope you guys can see my MATLAB screen. But then again, once I start sharing my entire screen, I cannot see your reactions. But anyway, okay. And then let me close all the graphs I have on screen. Okay. So I'm using MATLAB again, but you're not required to use MATLAB if you're more familiar and comfortable with other programming languages. That's fine. But I personally like MATLAB, so I'm using MATLAB here. Now let's start with the hierarchical clustering algorithm. Okay. Now, can you guys see well to my screen? I hope the font is fine. Or is it too small? Let me know in the chat if it's too small because I cannot see reactions. So just use the chat box or you can verbalize your ideas.
It's okay,
Fine,
son.
sir.
Okay, good. All right. So let's look at it line by line. So I'll start with the hierarchical clustering algorithm first. So in line 1, I am just loading a data set from MATLAB. So it's an intrinsic it's a built-in data set from MATLAB that you can use to explore data science algorithms. Maybe I'll just change my folder to this particular folder. There we go. Now, so in MATLAB, you can run commands line by line, so you don't have to run the entire thing. So usually for illustration purposes, or for debugging purposes, I run one line at a time so that I know what's happening. Or whenever I'm demoing a particular software, I run them one by one, all right, or line by line. So in MATLAB, you can highlight the line that you want or the commands that you want to be performed. You can right click on it and then click evaluate selection in command window, right? So only the highlighted commands will be performed by MATLAB. Or the shortcut, highlight it and then press F9. So here I right clicked and then I'll click evaluate selection. So now if you see in my workspace, though the text is quite small there. Sorry, I cannot do anything about that. But let me use my pen here. So you see here at this side, let me use red color here. In my workspace, it is now populated by two things, which is from the data file Fisher Irish. So it has a 150 by 4 matrix called MES, short for measurements, and species. We don't need the species structure right now because the species is the answer key, sort of. Because the measurement matrix here, it's a 150 by 4 matrix. It contains measurements of different specimen of iris, the flower iris. So there are 4 types of measurements: petal width, petal length, sepal width, and sepal length. So those 4 properties represents each of the columns. And then you have 150 specimen of iris. You have 150 sample, and then each rows of the matrix MES comprise of data from each of these specimen, right? And then each of the columns will contain the measurements. So you have petal width, petal length, sepal width, and sepal length. So you have a flower, you make those 4 measurements, and then you load those measurements into the matrix MES. So if I click on MES in my workspace, I click on it, and then you see here the data. Unfortunately, I forgot which column is which, right? Column 1 has this measurement 5.1 centimeters, 4.9 centimeters, 4.7, and so on. I forgot what that is. Is that the petal width, the petal length, petal width, petal length, sepal width, or sepal length? I'll tell you next time which is which. I just forgot it right now. And then each of the columns, so that means this specimen, right? The first specimen has measurements 5.1, 3.5, 1.4, and 0.2. Now, the idea is this measurements supposedly will give me an idea of what variety of iris that particular specimen belongs to. Because I have a gut feel that I can determine the variety of the specimen depending on some of these 4 measurements, right? And that's what really this structure species is for. So it is a sort of an answer key, and this should be invisible from the point of view of an unsupervised learning algorithm. So for instance, the first data point with measurements 5.1, 3.5, 1.4, and 0.2 belongs to the setosa variant. Okay. While the 77th with measurement 6.8, 2.8, 4.8, and 1.4, that belongs to the versicolor variant. So that's how this works, right? So these are data. But again, this is an unsupervised learning algorithm. So that means species should be invisible from the algorithm itself. So I will delete from my workspace species so that my algorithm cannot cheat, right? So it won't have any access to the species, to the answer key, the species answer key, right? Now, the next line number 3, just reshapes the measurement matrix. You can work with the entire measurement matrix mess 150 by 4, but say if I feel that only 2 columns are needed, so I can just erase the first and the second column and reshape it into a matrix X consisting of all rows of the measurement matrix. So meaning same indexing here. The first number inside the parentheses will tell you the row numbers. The second numbers will tell us the column numbers. When I write it this way, it means that X is equal to the measurement matrix, except that I will take all the rows. That's what the column means. I am taking all the rows, but I am only taking the third until the fourth column. All right. So meaning I am ignoring the first and the second rows. The first and the second columns. For reasons probably that I don't feel that the first 2 columns are necessary in clustering these data points. You will see later why I decided to do that. But if you don't have any idea, then you can just use the entire measurement matrix. But that would be more costly because if I run this, okay, I'll just highlight it and then press F9. The matrix X is 150 by 2. If you look at the workspace, X is 150 by 2. So it's a much smaller matrix and it should be faster to handle, right? Or computation should be handled out more easily. Okay. So that's the data pre-processing part. All right. So I just limited the data to what I needed. But again, you can play with this code later. I'll upload it together with the recording today. And then I don't know. Do you still need the notes or is it fine? But that's more of a scratch work, you know. So perhaps I can also upload the notes. You just need to decipher what it is because I didn't write it in a very detailed manner. But I hope you were listening during the discussion, so you will be able to fill in holes in that notes or in those notes. Now the actual clustering is done here in line number 8. So here, this line asks MATLAB to perform hierarchical clustering with maximum of 3 clusters and uses the average linkage. Okay, the average linkage is probably, this tells us how the distance between clusters are computed. Because remember, hierarchical clustering, we need to compute the distance between clusters. So this particular command tells MATLAB that, okay, the maximum number of clusters is equal to 3. That's what, let's do it step by step. So cluster data is the command. The first input should be the data that you want to train the algorithm with. So here I want to train it with just the vector X. I don't want to use the entire measurement matrix. Okay. And then the next input should be name arguments pair. So the name is maxclust. Maxclust tells us what's the maximum number of clusters. In this particular case, it's going to be 3, max of 3 clusters. And then linkage, this is telling MATLAB what type of distance to use whenever measuring distances between clusters. So the linkage, that's called linkage. the linkage should be determined by average. So average, you take the average of one cluster, the average of the other cluster, the distance between the averages will be the distance between the clusters. And then you can run this line. Okay. And then you'll have a matrix T, which is 150 by 1, and that predicts to which cluster, maximum of 3, your points, your individual points will belong to. So if you look at the workspace, there appeared a matrix T, which is 150 by 1. Okay. If I click on this guy, matrix T, so this tells us that, okay, specimen number 1 belongs to cluster 3. Specimen number 2 belongs to cluster 3. Specimen number 3 belongs to cluster number 3. Specimen number 104 belongs to cluster 2. Specimen number 97 belongs to cluster 1. And that's the prediction of our machine learning algorithm. Okay. Now, if you want to visualize the data, because nobody will be interested in looking at a matrix, right? So you want to make it a little bit more visual. So you look at lines 10 to 13. This will generate a group scattering plot using the results of hierarchical clustering. The X and the Y components will be the measurements. So this will be coming from the measurements. So the third column of the measurement matrix will be my X-axis. The Y-axis will be the measurements in the fourth column of the measurement matrix. Or I could have used X of column 1 and X column 2 here. So that's also fine. And then the third input would be the coloring. This will determine what's the color of the points in our scatter plot. Now, if I click on this, if I highlight this and I press F9, I hope I'm still here. I don't know what happened to my other device. It says connecting. But can you guys let me know if I'm still in the meeting?
Yes, sir. You're still in the meeting.
All right, thank you. Because my other device was disconnected. I hope my laptop wasn't disconnected. Well, it seems fine. Now, if I highlight the lines 12 and 13 and I press F9, then I will generate this plot, right? Again, in this plot, the X-axis corresponds to the measurements from the third column. Let me clear the annotations over here. So let me clear everything, clear all drawings, yeah. Okay, here we go, here. Sorry, the X-axis would be the measurements from the third column. And then the measurements in the Y-axis are from the fourth column. So that means this point, it has measurement probably 1.7 in the third column and 0.6 in the fourth column, right? And then the colors, the term is the grouping determined by hierarchical clustering. So that means this one, the yellow colors, probably they belong to the same variety. The blue ones probably belong to another variety, and the red ones belong to a different variety. So this is the clustering suggested by our hierarchical clustering algorithm. Okay. Now, is it correct or not? Well, I'll let you know on Thursday when we look at the answer key to this. All right, because I don't want to put the species data in the workspace because you might be thinking that the algorithm will be cheating. Right? It's an unsupervised learning, so we shouldn't have any idea about the clustering. Right? Hold on. Let me clear all drawings. There we go. Okay. Now, let me go here. There are a couple more, if you will allow me to spend another 5 more minutes so that I'll finish hierarchical clustering. And then I'll go on k-means and dbScan on Thursday. That means we really still need to meet Tuesday next week so that I can finish everything. All right. And that will be fine because I will also be giving you the last problem set on that day, all right? Linkage is basically this is a different method, right? But this does the same thing as hierarchical clustering, but it outputs a different structure. So the linkage command does whatever cluster data does, right? But it gives a different type of output. So the output L here, if you will see, I'll run this. It is a 149 by 3 matrix, which is quite different from the 150 by 1. And it doesn't actually make too much sense because why is it 149 by 3? The matrix T coming from cluster data makes sense to be 150 by 1. You have a 150 specimen, and that column gives us whatever cluster or what's the predicted cluster for each of the data points. But the linkage L, the linkage output, which is L, is actually in preparation for creating a dendrogram. So because here, this is how we see really the hierarchy, right? A dendrogram, the dendrogram command will not accept the matrix T because it is not in the right format, right? So it will only accept the dendrogram command for drawing the figure will only accept output from the linkage command. But the principle behind cluster data and linkage are the same. It's just they present the output in different formats, right? And the linkage command gives us an output that is ready for creating a dendrogram. I'll just press F9 here. And then here's the dendrogram for our data. And this illustrates why we said there are hidden, you can see the hidden structure between in the data. Because for instance here, yeah, we can say that these guys are grouped together. They belong to the first cluster. The second clusters are the second and third clusters are very similar to each other, that the hierarchy still thinks that they are part of the same cluster, but this is our second group or the second cluster, and this is the third cluster. But here we see the hidden structure between the clusters. Here we can see that it seems that the third cluster, this guy, can still be further broken down into subvarieties consisting of this group, and this group, right? So you can in hierarchical clustering, you can really discover underlying patterns in the data set, right? But unfortunately, by default, MATLAB only creates a dendrogram with 30 by default, by at most 30 data points. So here the x-axis represents each of the data points, and the y-axis the y-axis tells us the distance between the data points or between the trees in our dendrogram. So if you want to take a full look at the data set, right? So let me clear everything here. You can go back to the command. Then I think here you can put a second command, the maximum number of leaves in the dendrogram. So I say here 150 because we have 150 data points. And if I want to see all of them in a dendrogram, then I'll put 150 after the output of linkage. So linkage, then this will tell us the number of leaves in the dendrogram, or the number of data points that we see in the dendrogram. So I can just run lines 19 and 20, highlight it, then press F9. You will get this guy. And this is the complete dendrogram with all 150 data points in the dendrogram. Okay? Now, I still have 1 minute from the 5 minutes I borrowed from you. Again, you can play with some of the parameters. By the way, lines 15 and 20 are independent from the previous measurements. But let me just comment it so that this will not be part of what we'll be running. Because now I will play with the kind of linkage that I can use. So for instance here, let me just get the picture, right? So remember, this is, oops, why can't I resize this? There you go. So this figure one, this figure window here, this is the one when I use average linkage. But there are other types of linkages that you can declare. So for instance, this is the nice thing about the version 2022 of MATLAB. It will give you all the possible values for linkage. You can choose from average, which is the one we choose, the centroid, the complete, the median, the single, and the ward or the weighted. Many people prefer the ward linkage. So maybe I'll choose the ward linkage, but I didn't discuss what the ward linkage is, but I'll show it to you in a few. So the ward linkage is a possible type of linkage. And if I press F5, or if I press the run button over here on the middle top, right? If I press the run, the algorithm will run, and I will get figure number 2, which is the predicted clustering. And then say I compare it side by side with figure 1. Figure 1 is the one we obtained when we used the average linkage, while the left one, figure 2, is the one we get from the ward linkage. So you see slightly different groupings. The yellow group is not tainted too much because they are far from each other. But as we have seen in the dendrogram before, the second and the third clusters are very similar to each other. And graphically, they do look very similar to each other. So, and then if you compare the two, there are slight differences between clusters 2 and 3 from figure 1 and clusters 2 and 3 from figure 2. And that's the effect of different types of linkages. All right. So you need to pick which type of linkage or distance is appropriate for you. Now, if you want to explore what are the options that you can play with, so you can highlight the command in MATLAB. Any command in MATLAB, say the cluster data command, I'll right click on it. And then the third option from the drop down menu, help on cluster data, you can click on it. And then you will be led to the help center. And then you can open the help browser to see it in a more larger view. Okay. Let's just wait it to load. And this will tell you what are all the options that you have for cluster data. It's still, it has a description, so you can read the description over here. It has examples that you can follow. You can copy paste the command in an empty MATLAB script. And you also have the options here. So you have the option to declare the distance. If you want the Euclidean distance, the square Euclidean distance, the CT block, sorry, or the Taxicab distance, Minkowski distance, the Chebyshev distance, cosine distance, the correlation distance, or the Jacob distance. So you just need to put distance. What is the right syntax for it? Let me go here. Okay, so I'll just need to put distance in cluster data. So I'll add another name pair, name value argument here. Say distance, and then I'll choose what type of distance. Maybe I'll use not Taxicab. I'll use the Manhattan distance or the city block distance. It calls the Manhattan distance the city block distance over here. So you personalized the command here. That's fine. Press F5, and then we get this clustering. Okay, or you can use the cosine distance instead of the city block distance. If you use the cosine distance, press F5, definitely you'll get a different grouping, a much different grouping, because you see here, the distance is computed as the angle between vectors. So that means those that are lying in a straight line, they are considered to be closer to each other, as what we discussed earlier, right? The cosine distance. So be careful when using the cosine distance because it's really very different from the other types of distances. All right. So I'm 3 minutes over time now, so I need to stop before I consume another 30 minutes of your time. So we'll look at the program for the DB scan and the k-means algorithm next time before I introduce some classification algorithms. And that means we still need to meet on the 23rd. All right. And hopefully that will be our final meeting. All right. Okay. So any questions, guys? I know that's a lot, but you can go back to the recording later. I know I still owe you a bunch of recordings. I'll just have some job to do tonight, but I'll try to update everything in our webpage by the end of the week. If that will not be there by Friday, you can send me an email. You can spam me with emails so that I'll be forced to upload everything in our drive or in our website. Okay. So any questions or other concerns other than the files? Okay, so if
There's no,
there are none,
there's
yes.
no question, sir.
All right. So yeah, let's
And yes, sir.
go Stevens.
Uh, anyway, let me say thanks for the presentation. Not much of a question for now because we have to go over those things you have taught, practice those codes, and see how best we can use them. So thanks a lot for the lecture.
Yeah, you're welcome. So yeah, don't worry. I'll be uploading all the codes also and all the notes and the recordings, hopefully, because I'm recording everything on my hard drive because Zoom erases, I think, the recordings after some time, and I don't want you to lose access to it. So I'll upload it and I'll embed it in our website, but it will be on my YouTube channel so that you can go back to it whenever you need. So, sorry. Because probably next semester we will be using the same web page for this class. So when you go back, I need to delete everything, all the recordings that we have for this particular class. So you won't see our class recordings, but you can go to my YouTube page to see all the recordings for this class. I'll create a playlist, AMAT 255, and then I'll put the semester so that you know where to go. All right. Sorry about that. My voice is still not optimal this week. But yeah, thank you, Lynette, for letting me know. Yeah, probably some of you thought you'll be consulting with Sir Jomar today, but I haggled with Sir Jomar last week that I will handle the next few weeks, this week, and one more meeting next week. So that might be why there are some confusion, but it's fine. Recordings will be there hopefully by Friday, so they will not be missing anything. All right. And with that, guys, thank you for joining me today. I'll see you again on Thursday. Stay safe and have a nice evening. Bye, everyone.
Thank you, sir.
Thank you, sir.
All right.